So an operating system is software that is running on your computer that controls the execution of programs. So runs and gives access to the hardware of your system, to the applications or to the algorithms that you want to use. Okay. Whenever there is any word that you don't understand, just let us know. So Windows, as an example of an operating system, is the software that controls when Word has access to the hardware or when Excel has access to the hardware. So when Excel wants to save something on the disk, it does not speak directly to the disk. It speaks to the operating system that then has access and grants him its access to the disk. Why do you think that is? Why do you think there is a need for an operating system? I can think of a software that writes directly to the disk. The problem with that is that if I change the hardware, I need to change the software to be able to talk to that specific hardware, the new hardware that I have. So the operating system abstracts these functions and provides to the applications consistent ways of dealing with variable hardware. So the application asks the operating system, write this information to the disk, and the operating system will be made in such a way that if you change the type of disk, or if you change the size of the disk, or if you change the type of connector that is between the hardware layer and the software layer, then this complexity is hidden from the application, right? So it makes it possible to have an application that you can use regardless of the hardware that you are based on. Okay? This is why we need operating systems. Historically, operating systems were mostly concerned with graphics, so providing you the ability to display information on the screen, because you need that always, right? Well, in most cases. And you need disk access. That was the core function of operating systems traditionally. Have you heard of DOS?
Yeah.
Yeah.
Disk operating system. That's what it did. It allowed an application to write information on the disk. Now, the development of operating system is such that now operating systems are concerned with much more virtual memory. You don't only have the physical memory, you also have the concept of a virtual memory that the system stores on the disk. Oh, that's a problem though. Why do we have RAM? We say that. We have RAM because it's faster than the disk. So the concept of virtual memory is tricky. If I had exhausted my RAM and told the application that was asking for memory, sorry, you don't have any more memory to use, the only thing the application could do was to stop. So operating system currently try to allocate the memory to the applications that need it most and try to put whatever information on the disk that is not frequently used to make it sure that the application will not stop and will progress as fast as possible given the hardware. They will allow multiple applications to work simultaneously. Okay, now this is interesting. We have the concept of multitasking. Multiple applications running contemporarily. Now, this of course does not really happen. At the hardware level, only one operation will be executing at each time. So, us human being extremely slow, we don't realize that these applications are actually pausing and then starting again, and then pausing and starting again, and pausing and starting again, so fast that for us they just continuously flow. But it's the operating system that tells the CPU what to do next in order to make it look like they are all running contemporarily to us humans so slow we don't even have a clue. Okay? These custom file system, device drivers. So, device drivers are very interesting. If I have a mouse, an application might be interested in the position of the pointer on the screen and will ask the operating system to give it the coordinate of that pointer. Now, if I bring in a new mouse that has maybe one key more or one key less or has a different technology, I don't want to change the application to deal with all possible mices that are out there in commerce. So I buy a mouse, and they provide me with a driver, a software that is a kind of a plug-in to the operating system, that tells the operating system how to use that specific hardware. Okay? What is the catch with operating systems? Is that an application relies on these functions to be provided, okay? And there are ways in which the communication happens between the application and the operating system. There is some way in which the application can ask the system, tell me where the pointer is of my mouse. Tell me how much free space I have on the disk. These kind of abstract questions, okay? Then the operating system resolves to the physical layer. Now, these ways of asking such questions change from operating system to another. So, the way you develop an application for a Mac operating system is different from the way you develop it from a Windows operating system, because these ways of asking for functions of operating system are different. Okay? So what it's important for you to understand about operating systems is that whenever you have an application, it's going to be developed on one specific operating system. So you cannot run the same application on different operating systems unless the same application is developed multiple times. Okay? It's written in such a way that it can be tailored to work on multiple systems. So you have, that's why you cannot sometimes run some application on your Mac or on Windows, right? Because they're not being developed in such a way that they know the function that Mac can provide, or Windows can provide, or Linux can provide. So for your purposes, it's important to understand whenever you're dealing with a software environment to know what is the underlying requirements that it has in terms of operating systems as well. Okay. Maybe the hardware is suitable for running that application, but there is no intermediate jargon that the application and the hardware can talk, which is the operating system. Okay? I like this slide. I think it's very useful.
To gauge people's perception to another.
Exactly. Now, I'm sure you can't read anything on there, but you can certainly grasp the complexity of the structure of this chart. What this is a map of different software languages, programming languages that we have. It's not even updated, it's probably 2001 or something. So this is the history and of the development of languages. So Fortran, it's a very old language. from that, many other languages were born in time, and then at some point C was born, and C is somewhere here, and so on. So, what is a software language? What is a programming language? It's just a convention to allow somebody, a human, to produce an algorithm that can be then transformed into a code that can be executed from the machine. All right? And that's a very complicated task to achieve. Now, if I want to write a software that will tell me whether I need an umbrella or not, I can write it in a formalized way. I can say, if it rains or it snows, then get an umbrella. I can write this into a user interface on my computer, but we know that these can or must actually be transformed into a binary check of 1 and the OR function, which is a chip. It's a hardware, physical function that is inside the CPU. And this happens with in so-called machine language. So numbers that the machine can understand, where, I don't know, 34 means OR. Okay? So I need something to convert from this to that 34. Okay? And of course this is very simple, and sometimes things get much more complicated than that. So a computing language is such a thing that transforms some high-level statement written in a text from the developer into machine language. Something that can be executed directly on the hardware of your computer. Okay? So the reason there have been so many languages in time is because people thought, well, I can do better than that. I can think of a syntax or of a structure that improves my ability to write more complicated code, more complicated algorithms with less instruction, with less formalism, with less semicolons, with less or with more intuitive formats from the user, or with maybe a graphical user interface, or not necessarily typing code, but bringing together lines visually on the screen, and all sorts of things. Okay, but what we know is that at this point, all of this kind of fancy way of telling the computer to do something need to be transformed into read sensor A to know whether it's raining, read sensor B to know whether it's snowing, and then execute a 34 between them, and then light up a lamp somewhere if that's needed. Okay? So this is machine languages. This is what machine language is, and this is what computing languages is. It's a tool, a way to transform high-level, easy to understand from a human being statements into physical hardware statements.
What's, for example, the computer language we are using at the moment?
That's it, all of them.
All of them?
All the ones that you are still, I mean, this is probably when Fortran died in 1993. All the ones that you still, that are still alive here, they're still running. We have Java, we have C, we have C++, we have BASIC, all sorts of dialects of BASIC, we have Python, we have PHP, we have HTML, we have JavaScript, we have, you name it, we have hundreds. Now, the interesting thing is that we have libraries that can be sometimes shared across languages. So we have some subsets of functions that can be invoked from multiple platforms. And some of them only run on some operating systems, and some other run only on other operating systems, and so on. So it's really, really complicated stuff. That's why when I started saying, well, it's important to understand the infrastructure. On slide 1, we said there is an infrastructure, there is data, and there is people, and there is algorithms. Now, infrastructure is what we've seen so far. Two days from now, we'll be looking at software applications to convert from one format to another and so on. From now on, I'll go on. Today it's a long day, I'm afraid. But, I think it's useful for you to kind of have a breath of the complexity of the things that you're dealing with and probably recognize some of the jargon.
Sounds like Mr. Email has quite join us.
Okay, so we know what programming languages are. Learning a programming language. Do learn a programming language. Because if you don't, you will be stuck to what programmers can do for you. Don't become a professional, but get the foundations, get the basics. You will sort out so many little problems. I can point you to good self-learning resources for programming.
With PHP, it's better than making a website, I think.
I'm not partisan.
You know,
Nothing is forever in computing. Okay, now we are getting closer to the things that matter. Because when it comes to building information modeling, what is important for us is the I in between, is the information. I have a particular, because buildings will be there anyway at some point. And modeling is just whatever, something that we do. But information is what everything is about when it comes to building. So we now have a little window where we look at information, what it really is. Now, we have understood that computers deal with binary numbers. Okay? So, when do letters and symbols come in? That's a real question for you.
when it's been converted from binary to different language or
language? No.
Well, when it's converted from data to information.
Exactly, yes. When it's converted from data to information. Now, we haven't covered that yet. There is this idea that you have data, which is the underlying physical, and information, which is what you understand that data to mean. Okay? So, if we know that we only can deal with binary numbers, how do we work with letters and symbols?
Some language will change from information to
Some process, of course.
process.
The keyword not being language, but convention. We need a conventional connection. There you go, sorted. You make up a table where a number is associated to a symbol. And you must know that. If you don't know that, you can't understand a thing. So when you find the number 33, you know that the information that we meant to save was exclamation mark.
So we know the exclamation mark in binary.
Say again?
So technically, if you take it from binary to the encoding that you've done there,
Yeah.
we've wrote an exclamation mark on the in binary.
Yeah, true.
Yeah.
Yeah. Yeah. So, if you want to write something else, you want to write hello, you go and search for the age, 72. So you'll write 72. And then the next one is, well, I don't know. But we understood that if you want to store a single digit, single letter, we can rely on that conventional mapping. And if it's 84, we know it's a D. If it is 85, we know it's an E, and so on. Okay. Now, and this applies for a single byte. So what's a byte? We haven't said it, have we?
Single
No. That's a bit.
A byte is it not? Is it not?
So
It include it's a character. Well, no, it's not.
no, a byte is it's a group of bits. Okay. So a bit is a single binary digit. A byte is a group of 8 bits. If you think of it, it's amazing how people that deal with computers every day, have a telephone in their pocket, and live on Facebook, don't have a clue.
I don't live on Facebook. No.
But you live on some other weird techno space. Come on, admit it. Don't have a clue. You buy things on bytes, don't you? You go to the store and say, how megabytes is this?
Yeah.
And you're asking, so how mega glues is that? For you, it doesn't make a difference. You don't have a clue of what a byte is. That's amazing if you think of it. So a byte is a group of 8 bits. How big a number can you store on a byte? So how big a number can you store in 3 decimal digits? No, decimal.
Oh, decimal.
Yeah.
Okay.
Right. So we said it's 10 to the power of 3. How now? Back to the question. Remember this formula again. This is probably the only thing that is going to be useful for you in the future. Okay. That's why I come back to it again and again. How many numbers can you store on a byte? How many alternative options do you have?
8.
Well, a byte is 8 bits. So it's 2 to the power of 8.
Yeah, right.
2, 5, 6. So in a byte you can store 256 alternative numbers, alternative symbols. Okay? Now, all the letters in the alphabet, so 26 lowercase plus 26 uppercase plus all the digits from 0 to 9 plus commas, semicolons, exclamation marks, and a few others. Historically, people say, well, and plus a few that you don't, that are technically used from 0 to 33, 128 more or less. So, this conversion chart is such that you can comfortably store a letter in a byte. Okay? Make sense? So you have a byte, so you have 8 digits. And you can store a number there, 1, 0, 1, whatever it is, and you know that this equates to an A because you use that chart. Okay? So you need to have a byte available for storing that. Now, if we had 600 different words, or sorry, letters, okay, so let's say we are Chinese. You know they have more than 256 symbols, right?
Yeah.
They have something that looks like this and something that looks like this with a wiggle, all right? So they have thousands, okay? So if we want to store Chinese symbols, a byte is not enough. Okay? Because after some time you're going to have completed this map of 0 equates to A, 1 equates to B, and at some point you are 255 equates to something, and then I'm out of numbers. I don't have any space anymore to store another alternative symbol. So what do?
Group of bytes.
You increase the number of bits. Now, traditionally, you go in packs of bytes. So you don't add one more bit. You don't say, I'll just use 9 bits. You just go in packs of bytes. You will say, I'll use 2 bytes. If that's not enough, I'll use 3 bytes. But you must know that before you start. Why is that? That's complicated, but it's very, very, very damn important. Because all of this eventually is stored somewhere on your disk, right? So let's say you have something that tells you, well, you see kind of spaces on the disk physically where you have something that we know it's some physical value, but you can convert it to a number, right? And it can be 100111, whatever, 100111, whatever, okay, a byte and another byte. So if you want to read this information back to understand whether you say you wrote hello or goodbye, you need to know how to read that. So is it Chinese or is English? Because if it is Chinese, I need to read 2 at a time to understand what they are. Okay? If it is English, everyone will be corresponding to a letter. So this is convention. It's all on conventions. So whenever you have a file on your disk, what it physically is, it's only a stream of numbers. A stream of numbers. This is crucial for you to understand, okay? Whatever a file format is only just a stream of numbers. What you need to know in order to understand what the information is in that stream of numbers is what was the convention that was used to write it. There is no other way. So, was it English? I read every character and transform it into a byte using that table. Was it Chinese? I use another table that I've defined somewhere else, and I read couples of them to make this conversion. And there is no way to tell.
And who established the table?
Say again?
Who made the table?
Well, this one is the ASCII table. Have you heard of that before? American Standards for Computer Information, whatever. I made it up, but it must be something like that. Okay? So, who made this? Whoever was interested in creating a standard. Because at some point, people started developing their own hardware. And at some point, it was interesting to have ways to exchange information between different hardware. So people said, wait a second, this is all crazy. Let's make a standard that we can all agree to exchange text. So they came up with this. And at some point they say, well, wait a second, the Chinese now want computers. So they made another table, Unicode, that is capable of storing information in either 1, 2, or 3 bytes, and that contain if you're using Unicode, you can write in Chinese, Korean, Japanese, you name it. There is plenty of space in 3 bytes to store all the combinations for all the characters that we have on Earth. All right?
UFA in English, isn't it?
Say again?
UFA in English or something like that.
UTF, yes. UTF. now there are hundreds, literally hundreds of conventions on how to do that. But yeah, ASCII is the historical one. UTF-8 is one of the encoding that stores English characters.
I just remember Unicode when I was doing HTML5.
Yeah.
So.
Okay, so we now have understood something crucial. All of what we're dealing with now is conventional. All of it. Because eventually it's all down to ones and zeros, and they don't make any sense unless you have conventions that map it to some sort of meaningful thing for us. You remember that 1 means rain and 0 and 1 means snow? That was also conventional. It could be that this means fire and this means water, whatever. You don't know unless you have it into an infrastructure that reacts to that. So you connect this bit here to your fire alarm, if it is fire, and you connect this to your umbrella deploying mechanism, if it is rain. So what you do with that information is all conventional. File size. How big a file do you need to store a character A using ASCII?
How big a file?
How big a file do you need to store this? You know what a file is, I suppose.
Yeah.
Do you? I know we're taking it from the very grounds up, but there are things I will say in the next few days that need you to understand what a file really is. So we've said that the file is a stream of bytes. It's a stream of numbers, one after the other in ordered position. How big a file do you need to store character A?
8 bytes?
1 byte.
8 bytes?
8 bytes. So it's 1
8
byte.
bits.
8
1
bits.
byte.
1 byte. So it's possible, using this convention, to store this information in a file that is only 1 byte. Okay? Now, if you were to store a single character of the Chinese language using Unicode, how big a file would you need? 2 bytes. Okay? Now, if you were to write down AB, you would still need 2 bytes, right, in English. 1 for each. So you can store a character in each byte, but it's not enough because there are situations where we know that we need 2 bytes for a single character. How do you store a color? You know that there are ways to store colors, right? We might be interested in a color. Let's now bring it back to building information modeling. What paint should I buy?
There's some textures of materials.
Exactly. So how do I store that? Because at some point it will be stored on your disk. It will be stored on a file, right?
So by encoding.
By encoding it, of course, by some sort of convention. Can you think of a way?
1s and 0s.
Oh, of course it's going to be 1s and 0s, but how?
I know certain programs use hashtags in them. I might be going a bit too.
How could this convention work?
Probably, the colors are all in relation between the black and white. So if you take one number for black or number for white,
You could do that.
and you relate it by couple to make another color, so you can.
There's all sorts of ways. Let's think of one. I could write down in a file R-E-D. Right? I could write red down. Correct? This is 3 bytes. correct? Okay,
But if you want
but if I want to understand that, so if I want to understand that this means actually red, what do I need? I need somebody to know what red is. Because RED on its own, if you don't speak English, you don't know what color this is, right? So, and on top of that, that's complicated because if I have this much space available for storing a color, can I write yellow? That's complicated. So I can't really go and say, well, yes, it's yellow. Oh, I've finished the space I reserved for this information. I can kind of understand that. That would fit. That's yellow, right? So I could do it conventionally. But again, we are relying on some human ability to understand that this is some sort of color. Or we go down to some sort of physical properties of color. We have discovered that colors can be, all colors can be kind of separated in physical components. So we can make up a color that looks to our eyes as if it was original, based on the proportions of red, green, and blue that it has. You've played with this, I'm sure. You have played with sliders that change color in some editor, right? So you know that you have a slider that goes from 0. I need to get a new pen. So you have a slider of some sort that goes from 0 to 256. Is that familiar? Do you know why that is? It's actually 255, but yeah. So you now understand why it's all down to 255s. Why? Because you want to store that in a single byte. Okay, so we can say we can store a number by using 3 bytes and conventionally storing a number that goes from 0 to 255 as a proportion of red, green, and blue.
Then you go one step further and put hue saturation and stuff like that.
Ah, no, that's different. That's a different issue. I'll come to that in a
Because
second.
that's where you use a hashtag as well, isn't it?
Let's get there in a moment. So, depending on the proportion, on the relative proportion of red, green, and blue, you can compose any color of the spectrum. But that's not a miracle. That's something that happens because physically, that's what really happens. So if you merge physically colors in different proportions, you see different colors. And you can deconstruct this into the percentages again at a physical level. So, how many colors do we have? In the real world. In the real world, how many colors do we have?
Oh, loads. Loads.
Probably loads. Because wavelength and intensity in the physical world can be infinite, right? You can have a slide, and they will change and so on. But it's been deemed at some point appropriate or enough to store just 1 byte for the proportion of red, 1 byte for the proportion of green, and 1 byte for the proportion of blue. And so how many bits are these?
How many bits?
Equals X bits.
Go on, top your tongue. 24.
You're right.
Just trying to think, what am I doing?
So you have 8 bits for the red, 8 for the green, 8 for the blue. 24. How many different combinations can you store in 24 bits. Right?
You're not expecting us to work that out, right?
Yeah.
It will feel
That's 124, 124, 1, 2, 3 character, 124.
Yeah. 16,777,216.
Now, this might kind of demonstrate how old I am, but have you ever heard of 16 million colors? No. 10 years ago it was everywhere. This is a graphic card with 16 million colors. They were selling you hardware capable of addressing 16 million colors, also called true colors.
I've heard of that.
You've heard of true colors? That's equivalent. That means 16 million colors. Now, in nature, there are more than 16 million colors, but standards allow us to do this. Now, there are, if you open Photoshop, for instance, you can say if you want a depth of color of 8 bits or 16 bits for each of them. And that increases immensely the quality of the color that you can deal with, because you're not restricted anymore to 16 million colors, but you can have billion of colors. It's always going to be limited though, because it's always finite. That's important. That's what part of the things that you really need to understand, and that's why we're staying a lot on these topics. Whenever everything is binary, everything must be finite.
No, I was thinking about uncertainty, and I was just thinking about variable.
Anytime. Okay. So, once we have agreed on this standard of having 8 bytes per color, sorry, 8 bits per component per color, how do you store a picture?
Depending on the size, pixels, and stuff like that.
Yeah, the concept of pixel counting.
Because each pixel's got a different colour.
I'll let you go in 20 minutes. Have a long break, don't worry. So, how do you store a picture?
By colour.
Of course, by color of what? You answered it already.
Pixel.
Okay. A pixel.
And what if picture is not color?
It's always coloured.
No, she's right. There are pictures that don't have colors.
There is?
I'll cover that if you want. It wasn't planned, but that's that's the kind of questions I love. Now, a picture can be split in a bitmap code. So it's if you have your house there, whatever it is, okay, you split it, you cut it in chunks, and then you say, okay, what is the color of this? And it might be that it's not a single color, but you average it out. And you say, well, it is mostly blue, so I call this blue. Now, and you can express for each of them a percentage of how red or how blue or how green it is. Do I need to go deeper into this, or is this clear for everybody? So how big a file do I need to store a picture like that? It's the same question again and again. It's just I'm trying to bring you to understand what's really happening when you're dealing with these things. So what's really happening is that we need to store somewhere a color information for this. Color 1, color 2, color 3, color 4, color 5, 6, 7, 8, and 9. Makes sense. So we have a picture that is 3 by 3 pixels. Okay? And we need to store the color for each of them. Make sense? So, how big a file do we need?
27.
So we have, how much do we need for each single?
8,
So we need 3. How many do we have?
9.
9. So we're using 27 bytes. Make sense? For a 3 by 3 picture. Now this is tricky. Is that enough?
Depends.
Or what?
The end user. Depends if he wants to.
I'll ask you the question better. Are these 27 bytes enough for you to reconstruct a picture? You know, to go, because
No, it's not. It's not. Well, it depends.
it's not
on
enough for us to store that information. What we're really interested in is getting that information back, okay? The same for the letter. It's not that we want to write a 34 somewhere. We want to know that that meant A.
It totally depends on the image. I mean, if the image is the one in the foreground rather than the background, if you want to store just colours, yeah, that's fine. But if you want to store the image like that in the background, no, it's not.
No, my question is different. My question is, given these 25 bytes, can I reconstruct any picture that I have stored, so that I intended to store? It doesn't matter whatever it is. It's difficult to ask this question, I realize.
So can you store any picture?
Well, can you read back those 27 bytes into, and do you have all the information that you need to create a picture? It's very tricky. I'm sorry, I can't find a better way to answer this. I'll give you the answer, okay? That's what I can do.
No.
The answer will be no, of course. And the problem is that I have not stored the size of the picture, right? So I know I have 9 pixels, but I don't know how many are horizontally, how many are vertically. So let's say I have a picture that is 2 by 4, right? This is 8 pixels. And if I had a picture that is like that, 4 by 2, it's still 8 pixels. So when I'm reading them back, which one is it? Is the picture like this or the picture like that? You cannot tell. So before you can start writing the colors of each individual pixel, you must write something at the beginning of the file that tells you, well, this is a picture that is this big horizontally and this big vertically. You see the problem we're having here? Sometimes you don't write enough information on the file to be able to understand it fully when you're going back. So a good way to write that would be to use the first byte to store the horizontal size. Okay, so I could say 3, and then the vertical size 3, and then other 27 bytes that store each pixel's individual color. Now, after I've read the first 3, I move. So when I'm reading this back, I read this and I say, okay, I know that this is 3. So I read the second one and I know, oh, this is also 3. So I'm expecting now 27 bytes. And I start reading one after the other, 1, 2, 3, and I say, okay, this is the red component of that, the green component of that, the blue component of that, and then I move to the next. Okay, this is the second pixel, third pixel, and so on. I can do that. Okay. Now, we didn't store any information as to the picture should be read in this way or in this way. Right? So the second pixel, is it the one to the right of the first? Or is it the one on the bottom of it?
You don't know until you say coordinates.
Other two.
Well, do we need that information? Or can we do without that information?
You need the information.
You probably don't. So you can rely on a standard to do that. You can say, all the files that I save, all the pictures that I save, always go from the top left to the right until the line is finished and then move to the second line. But that's arbitrary again, it's a convention.
But
Alright?
that's known that whoever's trying to read it.
Yeah, so
They must know it. If they don't know, they have to try and make it up.
Or you
So,
put it-
file standards are all sorts of rules that people sit around the table and write so that everybody else can understand the content of a file. And they should sit around and think, okay, is that everything we need? Or is there some information that must be added for us to be able to, sorry, I hate when I do this. Is there any data that must be added so that the information can be extracted? Okay? That's tricky. So, you got this. A lot of conventions, a lot of common understanding and shared views to be able to go from here. Now, we have seen the concept of a bitmap. Okay? But if we are interested in storing a shape, a bitmap is not really very good, because I want a beautiful A. I want an A that looks like that. Right? I want it beautiful. And I want to be able to scale it up and down without losing quality. I want it beautiful. So if I happen to have it, produced down in pixels, this roughly, I cannot make it this beautiful again. I've lost all the information on the details and sophistication around the edges by saying, well, this is all black. Because it was mostly black. Okay? So, we can use some other concept. We can use the concept of a vector. We can use the concept of a line that goes from this point to that point, and then this point goes down, and then there is a line horizontal there at some point. So this is a vector graphics, that one is a bitmap graphics. They store the same information at one scale. They're both intended to be A's, but this one I can scale bigger, smaller, it will never lose quality. That one has already lost its quality. I can scale it down, but I'll never reconstruct the beauty of the original idea of an A that I had. Make sense? How do you store such a thing? I'm going to close. We are closing this quickly. Okay, don't be too scared. But I want to repeat this again and again until you understand the importance of file format, because that's going to be crucial for us.
Coordinate systems, points. So you set parameters and then
Yes.
you put coordinate systems within those parameters.
True. But that's not enough. How do I store this information here? With coordinates.
You don't set the parameters at first. So obviously 5 by 6.
We can say, okay,
And then that.
we can use a byte to say the whole size of the picture is going to be this much width
Yeah.
and this much height.
Yeah.
Maybe it's useful, maybe it's not. We don't know. What next?
I'm not sure if it's a coordinate system or line widths or anything like that. I don't know.
It depends. I mean, it's free to us to define a standard. Okay, what we are now doing, we are the ISO committee now, International Standard Organization, and we are defining a standard that everybody can use to store their vector graphics. We call this Northumbria vector format, NVF. Okay? What is the protocol, what is the convention that the Northumbria vector format uses? We make it up now, free.
Right. So
We can use like 2 bytes to define the direction, the vector, and after that the picture, the color of the picture
Right.
are inside that vector.
Wow. Okay. So let's say, okay, forget the idea of the pixel for the time being. We only want to store the vector. Okay, something like that. So the boxes around, we don't care, because we can reconstruct the boxes from the vector, right? So we want to store something like that. This is 0, 0. This is 2, 0. This is 4, 5, whatever. I'm copying it from there. But okay, coordinates. So we know that we have a 0, 0. We have x going here, y going there. All right. So you got it. We now want. Basically, what we want to describe is 3 lines. Okay? So, we want to be able to say there is one line that goes from this coordinate to another. And you correctly said we also want to say what color it is. So, we want to have 1 byte that says the color. Maybe, or 1 bit of information, one portions of information that tells you the color. So we could say we use 3 bytes to start with for the color. So it's red, green, and blue. And then we say we have a line. So we use 1 byte to store the idea that we can store a line, because we could actually be storing a circle. Right? So we have the concept of a line, and then we say what we need for each line is the starting point. So starting point, start ending point, start end. No, sorry, start x, start y. So the 2 coordinates of the starting point, and then we can say end x and end y. Right? So this is 1. This allows us to store a single line. Correct? So then, if we want to store the second, we'll use the same structure again, probably. So we'll have another red, green, blue, the concept of the line, the concept of a starting and ending point, and then the concept of, starting and ending x coordinate, and starting and ending y coordinate, whatever it is. So, this is 1, 2, 3, 4, 5, 6, 7, 8 bytes. So, another 8 bytes for the second line, and another 8 bytes for the third line. That's good. We have stored that information in these many bytes. Now, having used only 1 byte to store this x coordinate, gives us a limited precision in defining the horizontal proportion of this shape. So if this is my coordinate system, x and y, okay, the smallest number I can say is 0, the highest number I can say is 255, right? And I can specify 254 points in between. I cannot write 232.7. This level of precision cannot fit in 1 byte.
So it's finite.
It's finite. So that's because I only have 256 combinations. There is nothing in between, like I said. Makes sense? There is no concept of a comma in here, anywhere. Point something, decimal point. They're not there. We can live with that. Maybe we are happy with that. The point I want to make is that we must know then whenever we are defining a file format, we are putting in some constraints to what we can achieve with that. So we cannot achieve higher precision than 256 points horizontally or vertically. Okay? We could say we can use 2 bytes for x and 2 bytes for y and whatever. This allows us to be more precise. The same shape can be described with 256 decimals for each of them. All right?
I guess the goal, the aim is to reduce the quantity of bytes.
Generally so, yes. Because smaller files go fast, well, use less space on your disks, are processed much faster. They can send into an email easier, they can be shipped over the network faster. So the smaller numbers the smaller number of bytes that you need to deal with, the more efficient your system will be.
So it's a gap. There is a gap. It needs to be.
Well, it's an equilibrium, it's a balance to be struck. What is the reasonable precision for our purposes?
It's basically the BIM map is actually larger than the vector. If you use that if you're using the view.
There are some, and that's an interesting question. Which one of the two is the most efficient? Well, we know that the first one it doesn't scale, so we have some limitations in it. So the second one is much heavier, because if we had a fourth line, it would increase. So writing an H is heavier than writing an A.
But in its current format, it's actually smaller than the BIM map file.
No, the H is...
No, the EM.
Oh yeah, but the A. But you need to think generically for all the possible things that you want to store. So the A is cheaper, or same weight. The H is heavier. No, same. But the K is heavier, right? Because you have 4 lines. No, 3 again. Damn it.
The R. No.
The 8.
W.
The 8 is a lot of heavy. It's very heavy, the 8. Why is it a very heavy?
Because you've got each.
Because you have to split.
Yeah.
So you have a lot of lines. Can we be clever? Yes. We can increase our format so that the line is not the only thing you can store. So you go red, green, and blue, and then you say circle. And then 2 coordinates for the center, and one coordinate for the radius. Only two lines like that will give you an 8. Makes sense? Or only two records will give you an 8. One is centered here, and this is the radius. One is centered here, this is the radius. Okay? So file format are important, because if you have this file format, you'll have a lot of information to store an 8 by splitting down the number of lines into reasonably small fragments so that your eyes think that they are curves. But with this idea here, so version 2 of the Northumbria vector format, version 2, can produce better shapes with less space. It's a little more difficult to read, because you need to know that there is a concept of a line, there is a concept of a circle, and probably there is a concept of an arc. An arc is a circle that starts at some angle and ends at some other angle. Right?
You also say tangents as well, but then
Oh, yeah, splines.
yeah.
Yeah, cool. The next step is then, well, I thought I had another slide. Yeah. How do you store an architectural drawing? Just as we did, you have to have a format that will be capable of telling not only the color of a line, but the thickness of that line and the layer where it is on. And you've all used AutoCAD, I suppose, right? All of those information must be stored somewhere on your file. You have the concept of a text, you have the concept of a line, an arc, a polygon, an array of elements, and so on and so forth. Okay? They are not BIM yet. So how do you store the idea of a building? And now we are coming to what we really will be dealing with in the next few days. What if you provide that information to a computer? It can draw a schematic of a building for you. It will be able to draw a door in all of the details, filling, hatching, and design the frame of a door, and then whatever, draw an arc here, and the thickness and the handle and everything, but it will not know that that one is a door.
Just lines.
Just lines. Okay. Now, can you think of a format that will be able to store the idea of a door? I think we need a break. And I'll ask you the answer. We take an hour break for lunch? Is that okay? Can you cook?
I think it was about 4 hours.
Again, sorry?
See, I'm not sure what information you want. Do you want to rev it? That's.
Let's think of it for some
Or do you
time.
want it as low down as that? How would that one?
I want you to understand that whenever we're dealing with computer systems, we are dealing with what type of information we are interested in, and then how we encode it into the data layer. Okay? Because what we can do with it is a function of how it is encoded. Different encodings provide different functions, different things that we can do with that data. Okay? Good. I'll see you in 1 hour time, 45 minutes.
In the same room.
Yes, same room, but let's decide how long a break do you need? let's make it honest. I mean, if
I'm just thinking of break.
So
Not
that's
too much, 45 minutes.
45 minutes. So we'll meet again at 1:15.
got
Okay.
something like
If you need a longer break, you're entitled to it. Okay. Honestly.
Yeah.
Okay. 45 minutes. We'll meet you.
Are we gonna get the timetable today or?